Removing load-bearing walls in urban apartments. Risk, calculations, and compliance. Taking down a wall to open a kitchen, connect a living and dining room, or improve natural light is one of the most common renovation goals in city apartments. On paper, it looks simple. In practice, removing a load-bearing wall is a structural intervention that changes how the building carries weight. The design intent may be visual, but the decision is structural. In dense urban buildings, especially in places like Manhattan and New York City, load paths are continuous across floors and units. A wall that appears ordinary may be carrying floor loads from above, roof loads, or even transferring forces from other structural elements. Removing it without a clear engineering plan can lead to cracked finishes, sagging floors, misaligned doors, damage to neighboring apartments, and in extreme cases, serious structural instability. This article provides a technical but practical guide to load-bearing wall removal in urban apartments. It explains how structural engineers determine whether a wall is truly bearing, how loads are calculated, how replacement beams are sized, why temporary shoring is critical, how connections and supports are designed, and what additional considerations apply in high-rise buildings, post-tension slabs, and historic masonry structures. The goal is clarity. Open layouts are possible. They simply require disciplined structural work. Why removing a load-bearing wall is a structural decision. A load-bearing wall is part of the building's structural system. It supports vertical loads from slabs, joists, beams, partitions, finishes, furniture, and occupants. These loads travel through the wall into lower structural elements and ultimately into the foundation. This continuous route is known as the load path. When a bearing wall is removed, that load path is interrupted. The structural engineer's task is to redirect those forces safely to other elements without overstressing the structure or causing unacceptable movement. The replacement system must carry the same loads with adequate strength and stiffness. In older masonry buildings, walls often stack vertically from foundation to roof. Removing one segment may affect multiple levels. In modern reinforced concrete towers, interior walls may sit on beams or slabs in ways that are not obvious from visual inspection. Some walls are non-structural partitions, while others are integral to the system. Assumptions are risky. Determination must be based on documentation and investigation. Identifying whether a wall is load-bearing. The process begins with available records. Original construction drawings, if accessible through building management or city archives, are the most reliable source of information. Structural framing plans show beams, columns, slab thicknesses, and load-bearing walls. They provide context that cannot be seen from finished surfaces. When drawings are unavailable or incomplete, field investigation becomes necessary. Engineers examine wall thickness, alignment with elements above and below, and ceiling framing direction. A wall that aligns vertically with structural elements on multiple floors is more likely to be bearing. A light-framed partition running parallel to floor joists may be non-bearing. In many cases, small exploratory openings are required. Carefully removing sections of drywall or plaster allows the engineer to observe framing members, beam locations, or slab edges. In reinforced concrete buildings, non-destructive scanning equipment is often used to locate reinforcing bars and post-tension tendons before any cutting begins. Ground-penetrating radar and rebar scanners help avoid damaging structural components during investigation. The purpose of this discovery phase is to understand how loads currently travel through the building. Only with that understanding can a safe replacement be designed. Understanding the loads involved. Structural engineering converts physical conditions into calculated loads. The primary categories considered in residential apartment renovations are dead load and live load. Dead load includes the weight of structural slabs, joists, finishes, partitions, and permanently installed components. Live load represents variable occupancy loads such as people, furniture, and movable items. Building codes specify minimum live loads for residential occupancies, often around 40 pounds per square foot. Engineers determine the tributary area supported by the wall, the portion of floor or slab whose weight is transferred to that specific wall. By multiplying the combined dead and live load by the tributary area, the engineer calculates the total vertical load that the wall is carrying. For example, if a wall supports 120 square feet of floor area and the combined design load is 55 pounds per square foot, the total load equals 6,600 pounds. In real projects, Load factors and code-required combinations are applied to ensure adequate safety margins. Deflection limits are also checked to ensure that movement under service load remains within acceptable limits. Selecting and sizing the replacement beam. When a load-bearing wall is removed, the typical structural solution is to install a beam that spans the opening and transfers loads to supports at each end. In Manhattan apartment renovations, structural steel beams are common because of their strength to depth efficiency. Engineered wood products such as laminated veneer lumber may be appropriate in certain low-rise conditions. Reinforced concrete or composite systems may also be used, depending on the building type. Beam design must satisfy both strength and serviceability requirements. Strength checks ensure the beam can resist bending moments and shear forces without exceeding allowable stresses. Serviceability checks ensure that deflection under load is limited so that finishes do not crack and floors do not feel uneven. In residential renovations, serviceability often governs. Excessive deflection can produce visible sagging, cracked plaster, or misaligned doors long before structural capacity is reached. For longer spans, camber may be introduced during fabrication so that the beam appears level once loaded. Span length has a major influence on beam size. As span increases, depth and weight increase significantly to maintain stiffness. Designing supports and connections. A beam must deliver its load safely into supporting elements. The reaction forces at each end of the beam can be substantial and are concentrated over relatively small areas. Earring areas. If these reactions are placed on non-structural partitions or weak substrates, local failure can occur. Engineers design bearing conditions carefully. Solutions may include steel bearing plates that distribute load, reinforced masonry pockets, new steel columns, or connections into existing structural walls or columns. The supporting element must be verified to have a continuous load path to the foundation. Connection details include anchor bolts, welded plates, and bearing length size to resist shear, bending, and potential uplift. In existing buildings, conditions are rarely perfectly level or plumb, so field adjustments are anticipated in the design. Temporary shoring and load transfer. Temporary shoring is one of the most critical phases of removing a load-bearing wall. Before the wall is cut or demolished, temporary supports must be installed to carry the existing loads. The structural engineer prepares a shoring plan that specifies the location, capacity, and sequence of these supports. Adjustable steel shores or engineered frames are installed on stable bearing surfaces. The sequence of load transfer is controlled carefully. As the new beam is positioned and connected, loads are gradually shifted from the existing wall to the beam. Movement is monitored to ensure it matches expected behavior. Premature removal of shoring or improper sequencing can overload elements temporarily and cause cracking or settlement. In urban apartment buildings where adjacent units share structure, disciplined shoring is essential to prevent unintended damage. Post-tension slabs and concealed systems. In many high-rise buildings, floor systems are post-tensioned concrete slabs. These slabs contain high-strength steel tendons under tension. Cutting or drilling into a slab without locating these tendons can cause sudden release of force and serious structural consequences. Before coring or anchoring into a slab, non-destructive scanning is required to locate tendons and reinforcing bars. The same caution applies to embedded mechanical, electrical, and plumbing systems. Walls often conceal risers, conduits, and sleeves that must be identified before demolition. In dense urban renovations, scanning is a standard part of due diligence rather than an optional precaution. Historic masonry buildings. In pre-war or historic buildings, load-bearing walls are often masonry. Masonry performs well in compression, but is sensitive to concentrated loads and differential settlement. Removing a masonry-bearing wall requires careful design of bearing plates, grout beds, and temporary support. Engineers may specify larger bearing areas to reduce stress on existing brick or stone. In some cases, additional reinforcement or localized repair is required to ensure that reaction forces are distributed safely. Preservation requirements may also influence how beams are concealed or exposed. Regulatory and building approvals. Structural modifications in cities such as New York require formal approval. A licensed structural engineer prepares stamped drawings and calculations demonstrating compliance with the building code. Permit applications include structural notes, connection details, and shoring plans. In addition to municipal permits, cooperative and condominium boards require their own review. This often includes submission of structural drawings, contractor insurance documentation, proposed schedules, and protection plans for common areas. Inspections may be required at key stages, particularly during shoring and after beam installation. Failure to follow approved procedures can result in stop work orders and costly delays. Early coordination with the engineer, contractor, building management, and permit expediters reduces risk. Cost and sequencing considerations. Removing a load-bearing wall is typically one of the higher cost components of an apartment renovation. Costs include engineering fees, shop drawings, beam fabrication, delivery logistics, shoring equipment, inspections, fireproofing if required, and finish restoration. Longer spans and more complex support conditions increase costs. Unexpected conditions discovered during demolition can also require design revisions. For this reason, a contingency allowance is prudent. A structured workflow begins with investigation and engineering design, followed by permitting and building approval. Only after approvals are secured should demolition and shoring begin. Careful sequencing prevents rework and reduces disputes with building management. Documentation and long-term value upon completion. Owners should retain stamped drawings, shop drawings, inspection reports, and as-built documentation. These records demonstrate that the structural modification was engineered and permitted properly. In future sales or renovations, this documentation provides assurance to buyers and boards. Properly executed structural work is largely invisible once finishes are restored. Its value lies in stability and performance. When engineering is thorough, the open space feels effortless. When it is rushed or improvised, problems appear quickly. Removing a load-bearing wall in a Manhattan apartment is entirely achievable. It requires investigation, engineering, disciplined shoring, and coordinated approvals. The aesthetic goal may be openness, but the process is structural from beginning to end. How can I tell if a wall is load-bearing? You cannot determine this reliably by visual inspection alone. Indicators may include wall alignment with walls below, wall running perpendicular to floor joists, wall located near the center of the unit, thicker masonry or concrete construction. Only a licensed structural engineer can confirm whether a wall is load-bearing by reviewing building drawings and evaluating load paths. Do I need a structural engineer to remove a wall? Yes. In NYC, removing a load-bearing wall requires structural analysis, engineered drawings, filed plans with the Department of Buildings. Attempting structural demolition without engineering documentation is dangerous and illegal. What happens if a load-bearing wall is removed without proper support? Possible consequences include floor sagging, cracks in ceilings and walls, structural movement affecting neighboring units, stop work orders, DOB violations, significant repair costs. In extreme cases, improper removal can compromise the structural stability of the building. What replaces a load-bearing wall? Typically, a structural steel beam, wide flange beam, proper bearing supports at both ends, sometimes additional columns. The beam redistributes the load that the wall previously carried. How is the beam size determined? A structural engineer calculates tributary load area, dead load, live load, often 40 psf residential per code, span length, deflection limits, bearing conditions. Beam size is based on strength and serviceability requirements. Do I need permits to remove a load-bearing wall in Manhattan? Yes. Most structural alterations require alteration time 2 filing, licensed professional engineer plans, DOB approval, inspections. Additionally, co-ops and condos require board approval and alteration agreements.